Okay, chem nerds, we're going to go over kind of a gen chem topic here, so should be a good subject for a video. Can kind of breeze through it. It's not too math heavy, pretty common sense conceptually too. And that is kinetic molecular theory, which involves Boltzmann's distributions and phase diagrams. So let's get started. The basics of kinetic molecular theory, so that's what the KM stands for, kinetic molecular, is really pretty elementary. I would say everybody has a kind of a intuitive understanding of this, and it's a theory that describes why things change from different states. And so we've got all the three states here and the terms that you might use for transitions between all of these. Hopefully these are all terms that you already know. Subliming might be a new one. That's the direct conversion from a solid to a gas. I would also add that gas back to a solid is called deposition. But most of these other terms should be ones that you're familiar with: melting, freezing, evaporating, vaporization, condensing, all of those conversions. You probably also have an intuitive understanding that molecules in a solid are really not free to move around. They can kind of vibrate back and forth, and they're really close together. So you have a low kinetic energy and a small distance. As you move on up to a liquid, they're still really close together, but they have just enough freedom of motion that they can sort of snake past each other. This is why liquids don't have definite shape, but they're still close enough together that they have a definite volume. You pour a liquid into a different container, it takes on a new shape, but the volume is still the same. In a gas, though, they have such high kinetic energy, and they're separated by such large distances. They can completely fill up any volume, and they're completely free to move around. Okay, let's dive a little deeper into the math for this, and you'll see that all things being equal, solids have lower kinetic energy than gases, but it's a little more complicated than just that. From your physics class, you should recognize this as the equation for kinetic energy. And I'm bringing that up because I'm saying that temperature is a function of kinetic energy. The more the molecules move, the higher the temperature. Still pretty common sense there. Specifically, the temperature can be related to the average kinetic energy. So mathematically, we indicate an average with a bar. So an average of the kinetic energy can be related to temperature by this. I don't think this would be something that you would know. I'm pretty sure it shows up on your formula sheet. But this is the Boltzmann's constant, and that's temperature. So this allows us to go between kinetic energy and temperature. And this equation was derived by a fellow named Maxwell of electromagnetic frame and Ludwig Boltzmann, this fellow right here. And we get a distribution, which is what we're going to look more at than just the equations, of the velocity as a proxy for kinetic energy and the number of molecules that have a particular velocity. And they're a lot more easy to occupy low energy states for molecules, but as you increase the velocity, there's infinitely many more high energy states available. So the Boltzmann distribution is sort of a compromise between these two. It's easier to occupy low energy states, but there's a whole lot more high energy states to be had, so we get sort of a Goldilocks principle in between. The math behind this gets pretty heady, so we're not going to cover that at all, but just basically know that the highest point on the graph is the most probable molecular speed. the average speed is actually slightly higher than that, and it's skewed because this tail of the graph is bounded at 0, and this tail of the graph is an asymptote that, I'm not going to get into like speed of light kind of things here, but it's approaching infinity. So that's why the average is skewed slightly to the higher, but normally what you'll see is we'll discuss that this most probable speed would be the speed that you would plug into the relationship for temperature in your average kinetic energy. So let's look at, and this would be kind of an applicable question, if we kept everything constant but we changed the temperature, what would happen to the Boltzmann's distribution? And this would be a kind of question that I would use. I would give you the Boltzmann distribution at a particular temperature. Maybe I gave you this one at 300 here, and I would ask you to sketch or to select the distribution that correctly matches a higher or lower temperature. So there's two things that I want you to notice. The easy one is the peak value. So at higher temperatures, you notice that the most probable speed changes. So at high T, higher most probable speed. So if you were asked to select a distribution for a higher temperature, you would want to make sure that if I gave you, say, this 300 distribution right here, you would want to select a distribution that has a peak at a higher speed. If I asked you for a distribution for a lower temperature, you would want to make sure that you pick one that has a peak at a lower temperature. The other thing that you need to notice, and could be incorporated into your question, is sort of what happens to the shape of the distribution. And that is, at higher temperatures, you have a more broad curve. And that's because there's more energy states available. So if you recall on that previous slide where we had the curves, as there's infinitely more higher energy states to be occupied. So as you increase the temperature, not only does your peak shift to the right, but your curve sort of broadens and flattens out because there's more higher energy states that can be occupied. So that sort of flattens your curve. Whereas at low temperature, the peak is to the left and the curve is very compressed because it doesn't have enough energy to occupy these higher energy states. So all of the molecules are confined in a much more narrow band. So on this kind of question, what you'd look for is, if I asked you for a higher temperature one, you would need to make sure that you accomplish two things: that the peak of the graph is at a higher speed, and that you select one that is more broad. A really good distractor on my thing would be to put the same shape, but just sort of shift it, equally, but just sort of shift it over to the right. That would still be wrong because you need to select something that is also broader. And if I asked for a lower temperature, you would need to accomplish two things: that the peak is further to the left and that the band is now very narrow. Okay, moving on. The other thing that I might ask you to compare is a Boltzmann distribution if we keep temperature constant, but we have a different molar mass. So remember, here's mass. So if the mass increases at the same kinetic energy, because we're talking constant T, so same Ke. So if we are upping the mass but keeping the kinetic energy the same, that means your velocity must decrease. And you can see that in the equation for the velocity actually on the curve, the root mean square velocity. It's in the bottom. So if we increase this, again, the velocity has to decrease. So if we compare hydrogen, a very low molecular mass, to oxygen at the same temperature, the value for its velocity needs to be lower because the mass value is bigger. And like on the previous slide, as you go to lower velocities, your curve needs to get narrower too. So make sure that you accomplish both of those things. So a higher molar mass means lower most probable velocity and a more narrow distribution. Okay, so that basically kind of covers all the questions that I might ask you as far as Boltzmann's distributions. I'm not going to ask you any math for these. Everything is just going to be really conceptual about either here's a distribution, what would this look like at the same temperature with different mass, or here's a distribution, what would this look like, same mass, different temperature. So be prepared to answer both of those two questions. We lost that a little bit. Let me move this. All right, now on to phase diagrams. So if you think back to what we discussed earlier, we had the solid, liquid, and gas. So these are the states that you can interplay between. And I think everybody understands that as you increase temperature, you increase the kinetic energy. So increasing temperature tends to favor gases. But now we have another thing that's going to be involved, and that is pressure. Because the other side of the kinetic molecular theory is the distance between them. So as you increase pressure, you decrease the distance. And that tends to turn things into solids. So high temperature favors the gas state. High pressure favors the solid state. So that sort of begs the question, well, which wins if we have high temperature and high pressure? Where exactly does it pan out? Does it make a liquid? Which one wins out? And so for every substance, it will have a unique phase diagram. And when I say unique, these boundaries differ, but the shape is always the same. It's always sort of this Y shape, solid, liquid, gas. And that's because as you increase temperature, you favor the gas state, and as you increase pressure, you favor the solid state. So the exact slopes on these lines will differ, but the parts will always be the same. Two other points on this that I need to point out to you. Triple point. This is the state where this is kind of like that place out in the four corners of the U.S. where you can be in 4 states at once. Here you can be at all 3 states at the same time, and you'll be freely interconverting between gas, liquid, and solid. I'll post a link to this, but the best YouTube video is if you search for the triple point of tert butyl alcohol. I'll put a link for this down in the comments. This is the most common triple point demonstration to see, because its triple point temperature occurs very near to room temperature. So the only thing that you need to change is the pressure. So check that out. It's kind of a cool video to watch. The other point that I need to point out is this, and this is called the critical point. And it is there because at very high temperatures and very high pressures, you can no longer distinguish between liquids and gases. So it is what we call a hypercritical fluid. So if you go in regions above and to the right of the critical point, it is a hypercritical fluid. All right, so let's look at some of the things that we can do with this. It allows us to predict sort of what changes would occur if you increased pressure, increased temperature, whatever. So let's say that we started with a very low temperature. So we started somewhere over here. So we would be a solid. And as you increase your temperature, we would be moving right. So we take some ice out of our freezer and increase the temperature. And so you see that you would just have a line going across here. So you'd get transformation solid, liquid to gas. If you were below the triple point, you would not have the liquid state as in dry ice, and so if you're in regions down here, this is where you can get the sublimation. So if your pressures are below that of the pressure at the triple point, it's impossible for you to have a liquid. You can just interconvert between solids and gases. All right, lastly here, let's look at this if we change pressures. And this is not to scale. If these are drawn to scale, this line looks very nearly horizontal, but it would have a slight positive slope. So that's why I've selected this image, because it kind of emphasizes that. And that is if we start at very low pressures and we increase the pressure at constant temperature, you would see that we would go from gas to liquid to solid. So this is saying that this is our lowest density, because we would be starting at the lowest pressure, highest distances between them, and lowest density. And solid would have the highest density. And this is true for most substances, but water. Water is very unique. It is one of maybe 5 things out there, and some of the other exceptions are particular crystal states of other metals, so not something that you're likely to become encounter with. Most people don't encounter like ortho-arsenic crystals on their day-to-day existence. So water is a very, very important exception, and it has to do with water's geometry and the fact that it's a polar molecule. So help me if you forget that water is bent and is very polar, I don't know if there's anything I can do to help you. So because water is polar, when we have lots of water molecules around, they try and form hydrogen bonds between them. But in the liquid state, because there's too much kinetic energy, these hydrogen bonds are constantly forming and breaking and then reforming. So we can't get like a nice crystalline thing. However, in ice, you can see here, the kinetic energy is much lower. All our molecules are doing are just sort of buzzing around and not freely moving like in the liquid. These hydrogen bonds can form and be stabilized, and because water has this V-shaped geometry, we can get this crystal lattice. I mean, this is very ionic substance like, to where these hydrogen bonds can form sort of a link all the way through the entire thing. So I would ask you, normally we associate solids as being the most dense, but which of these looks to be the most dense? Clearly this is the most dense. When these hydrogen bonds form, you have all of this empty space here. So this is the lower density, which explains a couple interesting things about ice. Why ice floats, whereas most solids would sink in their corresponding liquid. And it also explains, and this is kind of the cool part, why ice is slippery and other solids aren't. And it shows up on its phase diagram. So notice the difference here, and the main difference is this line is now negatively sloped. So big thing to know here, the difference between the phase diagram of most substances and the phase diagram of waters. Everything else is the same, except this line needs to go back to the right. And the reason that is, if we go back to our previous slide, think about which of those states is the most dense, and it's the liquid, which means if we compress our solid and decrease the distance between them, it actually turns into a liquid. Whereas for most substances, when you compress on the liquid molecules, it decreases their distance and turns them into solids. So for water, the liquid is the most dense. Very unusual. So if we put pressure on solid ice, so if I start with some solid ice here at low pressure, and I apply pressure to it, my ice will turn into a liquid, because as I decrease the distance between the molecules by putting pressure on it, it's going to turn into a liquid state. So if we have some ice and you were to step on it, what happens is the surface layer here actually, because of the pressure of your foot, turns into a liquid. And so you have a whole bunch of like little bitty liquid water ball bearings that form on the surface, which is why ice is slippery. As soon as you remove your foot, they refreeze. And so this is why ice is slippery, whereas most things aren't. And it's also why ice floats, whereas most solids, if you throw them into their corresponding liquid, don't. So to recap some of the things that you need to get out of this, you need to know about Boltzmann's distributions for changing temperature, increasing the temperature, higher thing, broader curve, decreasing the temperature, lower point, sharper curve. I should probably make that extend higher. And the differences between Boltzmann's distributions for molar mass. So this would be the lighter mass versus the heavier mass. And phase diagrams. Most phase diagrams have this rightward slope, solid, liquid, gas, where the solid is the most dense state. Water has a negative slope, liquid is the most dense state, and that's because of hydrogen bonds. So, have a good evening, folks. Oh, almost forgot. I'll provide some links down into the comment section on this for some relative parts for this on the Chem Wiki page from UC Davis if you want to do some additional reading. All right, later.